Welcome back to another episode on the Delta Potential. We're back with another episode on the build series of a Automotive LIN Network. We're on episode 5. So today we're going to continue with the next implementation block, which is the MCU. That's going to be very, very exciting to get started with that. The whole core of the PCB. So we got the power management on block, and next up is the MCU. And we're gonna follow the guidelines for it. I've actually selected a component that we will use for this. And it's from NXP, and I will show the component here. So an S32K1 microcontroller. So this is basically one of their Automotive 32-bit microcontrollers, ARM Cortex-M based MCUs. A cryptographic security engine, high performance functional safety. So this is compliant with ISO 26262, which is a very important standard in terms of automotive. It goes up to ASIL B. What else? Suitable for both AUTOSAR and non-AUTOSAR applications. So we'll be doing some non-AUTOSAR, obviously, in the future. Here we have the data sheet, and I will open that. We're going to follow basically this document. Should be some more. Anyways, this document, the data sheet, and also the application application note. Power modes configuration. Okay. Now, but this thing has everything that we need. And we'll go down here to a block diagram. I mean, it has a lot. Of course, and we will go through a lot of them, but for the time being, all we know is that we need a LIN network, and I think it's this one, the low power UART, that can be configured to LIN, meaning we have a LIN controller that we can configure. Yeah. So, but I'm also learning all of this, and it's going to be fun going into details on this. Let's go further down. Feature comparison. So here is all the features in different modules. So system, memory, timer, analog, communication. Communication, for example, we have on this specific chip series S32K11X, and we will go for 1116, I think. That's up to a number of IOs up to 43. Wonder if that is the 48 package done, and this is the 64. So maybe even the 18. But we can see how they differ. So the filled-in circles is what is implemented, and then the empty circles or non-filled circles is not implemented. So frequency 48 megahertz. This core M0 plus. Peripheral speed up to 48 megahertz. Watchdog, one watchdog. Memory protection unit, watchdog, low power modes. Supply voltage. Memory, flash, RAM, Flex RAM cache. There's no cache in this. Timer. So there's a lot of these things I don't even know if we need, right? Or I should maybe also show my screen so you can see. This is the data sheet for the S32K1 series. This is the chip we're gonna use. So either the 64 quad flat package or the 48. There's also 48 one. Let's go back here and check. So we don't really need to go into all the details. There's some analog inputs too. So ADC, 12-bit SAR ADC. Even an Ethernet not implemented on this one. The higher module has it, but not the one we're selecting. We don't need Ethernet for the time being, but it's good to know that if we upgrade a little bit, we'll be able to access Ethernet as well. It has Flex CAN, so CAN interface, and we can also configure that to be flexible data rate CAN, so a slightly higher data rate or speed. Flex IO, 8 pins configurable as UART, SPI, I2C, I2S. Low power UART or LIN. We have 2 of them. We can actually have 2 LIN nodes or 2 LIN networks if we want. Here's the Ethernet serial audio interface. Debug, serial wire debug, JTAG, and the ecosystem and the packages. So on this one, it's actually up to only 48 pin. And then here it's also up to 64 pin. So probably because that added other SPI. What else? A few extra. Or what is this? No, I don't know. But yes, so we start there. We don't really think too much about it. We start very modest and simple. So select components. So NXP S32K 116. Here we want a debug interface. If that's connector, serial wire debug, or JTAG or something, we'll have that. Then we'll have a crystal, of course, coupling capacitors and all that stuff. But I just for now just add the most essential, the chip itself and these things. We of course have the 3.3. We also have a 5 volt. If we want to power this thing from 5 volt, we can do that. Although I think maybe 3.3 is better. I don't know. So here's the data sheet. Just a bit curious. If I go down to the documentation, check all the application notes. This one we have open. Microcontroller troubleshooting, optimizing, cookbook. Check that one as well. But this is more software. bootloader. Differences between this and newer versions, I guess. Or beefier versions. Understanding injection current on NXP Automotive microcontrollers. Injection current, maybe that's the EMC or like the EMC test and stuff. I don't know. Go back. Clock robustness. Power management for S32K1. See what is written here. This is the power mode. HS run, sleep, deep sleep. It's way too specific at the moment. And it's more related to software. Okay, let's see. I need to prepare the block implementation template. It's gonna be a bigger one to handle. But we did the same thing for the DC-DC buck converter, the linear drop-off voltage regulator, and then next up is the MCU. Then we go through all the all the pins. Power mode. Reference manual. So this is also a bit more related to software. Maybe program partition. Yeah. Okay, let's go through the datasheet first, and we'll go through the pins and everything. Goes up to 5.5 and 2.7 to 5.5. Voltage and current operation requirements. We'll power it with 3.3 at least, I think. Typical conditions assumes VDD is equal to 5 volts. Or maybe 5 volt then. Minimum. Oh no, that's stars. Yeah, maybe we should do 5 volts then. Good thing we have that output. So we said we'll start with this 48. What is it? Low quad flat package? Oh. LQFBE package. Just remember what the name was. Low profile quad flat package. Thin surface mount. Yes, sir. Thinner than standard quad flat package. Okay. Very well. So we'll go for this one. Near its outline. You know, typical values for coupling capacitors, ADC reference high decoupling capacitance. For improved performance, it is recommended to use 10 microfarad, 0.1 microfarad, and 1 nanofarad capacitors in parallel. Close as possible. Fair enough. Power consumption. I need the I/O signal table as well. Or maybe I should use the 3.3 volt. I guess you can also do that. DC electrical specifications at 3.3 voltage range for S32K1. Okay. Input capacitance. So wire debug. And I also need KeyCat open. And +3 V3. I don't know yet how I should use this properly actually. For instance, here place sheet bin. So we have 3.3 going to the MCU. And then maybe 5 volt goes to the display, who knows. Let's say for the time being, this is how that works. So now we work on this. And now we actually need to start with making the symbol. NXP, MCU, just to see a little bit. For example, this one is a low profile quad flat package 48 pin. Can use that as reference. Copy. New library for this project. MCU. Core. Maybe core. And then MCU. And then S32K 1116. LQ. No, just like that. So core. No, I shouldn't have named it that. I should only core and then MCU, and then inside we create a new symbol. Or actually we paste the symbol. And then we rename it to S32K 116. And then here we can, package is correct, pretty sure. S32K 1116. So we, okay, 28, that's the 32 one then. But we're using the 48 pin. Let's go over here. So this one. Seven 0.5 millimeter pitch, 7 millimeter, 77 1.4. Is just a height then, which is that low profile. Low profile quad flat package. Yeah, so it's correct package. The data sheet we can change to that one. It is a 32-bit ARM Cortex M0. Maybe instead we 0 plus. Can copy this. So. Now the question is all of these pins are bidirectional power inputs, input output, power input, this is the ground. So this might not be correct, obviously, so I need to check that. What's the difference of these two? Pin count. Here's another SPI compared to this one. A bit more memory on these. So we select this one, 116, 128 flash, 16 RAM, up to 42 IOs, 4 channel EDMA, 1 flex CAN with 1 FD, 1 13 channel 12-bit ADC. Common features. $5V, ASOB capable. About $3. Cache notes. Series cookbook. Let's it's good you have all this information at least. Programming Flash, Flash programming best practices. Okay, application on software. No. Ah, here you go. So, I/O signal description 16. Yeah. Where should I put all of these? Okay, I'll make a file for it. Core. Oh, it's Automotive LIN Network project files. I/O list. So yeah, you can also see, put it here. Ah. Da, 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 da. Yes. So I put it in here, so this document that is added to the user manual, I think. Or is it the reference manual? So you can see the pinout and see what they're doing. So this one we can hide. It's nice to just relax and do some electronics. So this one can hide. I guess. Maybe I put it like this so I don't forget it. But this is a different package, so it doesn't really apply to us. I think I will, yeah, I think I will hide it. So this is the package we're using, 48 low profile quad flat package. Then we have the pin names and what they are as a default, and then they can be configured to something else, as far as I understand. So for example, these two are disabled by default, pin 3 and 4, but they can also be CON, TX and RX, so the input from the CAN transceiver. We're not using any CAN transceivers now or any CAN network, but pretty sure we'll add one in the future. So cool, but then we can go through this list and I can add into my list and put what we configure. What do we need? What do we don't need? We should also look at how, if there's an image, yeah, like this. So we can kind of already now see where we should put the different things. So pin 3 and 4 are here. They're unused, but they can also be CON. Pin 4, no. 8, 9 is for the crystal. 8, 9 is here. Power ground, power ground. And sometimes when I'm working on things like this, where it's a little bit overwhelming, everything, it's so easy to just doubt yourself and you stop and you think, damn, just going through this list of 48 pins, it sounds like a lot, but it's really not that many in the great scheme of things. Now we're using a quite compact microcontroller compared to a lot of other things on the market with up over 200 pins, right? With a lot more functionality. And we're only focusing on power ground, crystal, debug interface, a LIN network or LIN controller, and then maybe some IOs for a display, without knowing that what I use. Is that a SPI channel maybe, or I2C? I don't know. We'll get to that. But when things get a bit overwhelming, just breathe. You know, it'll be all right. We'll just start, and as we progress, we'll see that it wasn't that hard to begin with. I will add all the abbreviations. Insert. There you go. Perfect. Down to 48. So And I don't think we really need to know the abbreviation for this. We do need to update our schematic, so our symbol, and add all of these. That we can do later. First, let's set what the different pins are, and then we can, you know, create our symbol, make our symbol the best for our project. That is nice. Okay, I will maybe put, or I'll put this over here, this on my other monitor. Then I can look at that side and then input here. Disabled by default. Maybe I should also add a default pin, what they are on this one. Default, yeah. And then I want to highlight the pins that we really need to know. And maybe I can add a rule or something here if it's possible. Oh, how do I do that here? If I can. Apply to range. Text contains disabled. Format cells if color scale, single color. D7, D14 to 61. Can I do it like that? No. D14. Then it's green. D61. How do I do it? Select the data range. Okay. So whoever is disabled, okay, that did not work. D14, D61. Google Sheet, add range. Define name range. Okay. S32K16. Default pins range. Okay. Yeah, that's how you do it. Okay. Could I also add this though? No. Text contains disabled. So. Is this blue? Oh. So. Then we don't see them so much. We see that it says disabled, but at least we separate them a little bit. So these are power pins at least. This is ground. I would prefer that to be black. Those two can just be white. So then that's power, ground, and a crystal. On the left side of the footprint. So kind of like the input, maybe. Okay, so what is the alternative to this one? Or what is this really? Pinout. Oh, signal table. So we're at 13. So 13 is the one, or the next one that is not disabled. These can also be configured to be SPI, one of these or two of these. 10 and 11 can also be configured as SPI. So those two. Sane, or what is it? Clock. Component O in 3 CMP. Okay, pin 13. PTE. PTE 8. Comparator input signal. So it's a comparator input signal. Unused question mark. FTM channel. So it's not disabled, but it can be disabled. Port E IO channel. No, what? How do I read this? FTM channel, comparator input channel signal. And what is a FTM channel? Okay, we skipped that one. Unused comparator input signal. So this is the implementation. Power analog, ground, crystal in, crystal out. Not sure if it's which one is in or which one is out, or if it really matters. This one. So here also FDM channel. Clock out. Clock out. 1415. S out PC. So these two can also be SPI, PS. I don't know what that really means. A chip select, of course. And this is S out. So it's actually good to set it up like this, because then I can know if I need an SPI. I know that these can be configured to be that. So pin 10 to 15. And then I can check on the 10 to 15, that's right at the corner of this package. So I'll show it here as well. 10 to 15 here. Meaning if we have some device down here, doesn't really matter, but we can optimize our pin out so that it makes it easier for us during the layout. Okay, I move it back here again. So that can be configured as SPI as well. And also this one, clock out, chip select, and also the key out, question mark. Then here's some ADCs inputs. That's pin 16. The two above is disabled. 16. So we're already at 16 and we have 58 pins. So 16, 17, PTC 3 and 2. PTC 3 and 2. PTC 3, port C, IO, FDM channel, CAN TX channel, transmit, UART pin, transmit, ADC, single-ended inputs, and comparator input signal. So it can be configured as that. By default, it's PTC3, PTC2. No, I think I read that correctly. Yes. ADC or comparator input signal. ADC single-ended. Ended input can also be configured as PTC3 and 2 FTM channel on our X UART GX. That goes for this too. Although on the PTC2 is RX and then TX. PTC2 is receive. And then here is TX. PTC3 transmit, yes, and TX. Yeah, that's how you gotta do it. So this could be interesting for the future. So we have that also ready. Make it blue. Other than that, it's ADC channel. Then it's disabled, and there's a bunch of ADCs. Okay, it's the 12 pin, the 12-bit, I guess. Yeah. So here, ADC single-ended signal. So that's all of these. This hits this. Ground. Power. So by default, we don't really have that many pins to work with, which makes it easier for us, but we still have a lot of capabilities. Okay, let's check what pin 19, what else they can be. ADC, they can be con. So 25 can also be configured as con 0 GX UART. And even SPI as out. (26) RX, and then UART is also receive. SPI is chip select 0. Chip select 0. Because there was chip select 1. Wait, what is T clock? PTB 1. External clock input. FDM external clock input. '23 and '24 can also be configured as SPI. 23, 24, SPI as in, and as clock. So the same as these two, 10 and 11, 23 and 24. Real-time clock in 29. As RTC clock in, I'll be UART1 RTS. This could maybe be interesting. Make it orange. FXIO on pin 33, by default disabled. PTD 3. FlexIO. FlexIO. Also be configured as FlexIO. So that goes for all the way down to 36. Yeah, we have even I squared C on 35 and 36. I squared C SQL. I squared C SDA. That's also good to know. of course, when we're working on this later on in the code studio, we can also, they have a graphical interface or that you can use to visually set it up how the pins are configured. So I actually should download that as well. But we're not doing layout just yet, so we don't have to stress with it. $37.38 ADC. What is this? PTA 1 secondary data. I2C secondary data IO. Request to send. UART. So 3738. It can be configured to a lot. Request to send. Flex IO. I2C STA secondary data, and then here it's CTS, whatever that is. Request to send, say to send. Yeah, okay. You should charge my headset. Keeps dying. There you go. What did I say? So clear to send, clear to send, clear to send. Request to send, clear to send. So by default, they're inputs. So PTE, example PTE 5. No, PTE 8. By default, an input. By default. Okay, we're down. Or let's check these two. 39 all the way down to 44 are disabled by default. They can also be UART. An FDM channel. So 39 and 40. UART 1 TX RX. Okay, this is not correct. 38 and 37 is UART 0. So I guess there's 2 UART channels. Check the data sheet real quick here, maybe. Communication UART 2, right? Makes sense. So we can have 1 UART and then 1 LIN. 2 LIN, 2 UART. Since we're building a commander or master, we need one of them for LIN. And what is this? PTC7 FDM quadrature decode phase. Phase A, phase B, never heard of that. It's default, or disabled by default. It's really cool, actually, multiplexing that you can, configure the pins to alternatives, relevant alternatives. So, and then we can, that's the alternatives that we have. And then we can write what we do. What's our implementation? Okay, the rest of these 42, 43, 44. Also comparator RRT, whatever that is. FTM. Okay, bottom is at least clear. 44 to 45, JTAG. TDO, TDI, JTAG, T clock or zero wire debug clock, and zero wire debug DIO. And reset. Reset B. PTA5. Reset IO system. PTA. reset IO. I mean, JTAG test mode select or 0 wire debug data IO. JTAG TDO. JTAG test data output. JTAG clock or 0 wire debug clock. T clock. Test clock. So okay, now we're kind of gone through the whole list. Close the implementation here. Here's our external component selection. We might have to break this up into modules. So all of these are connected to some modules. For example, power, I guess it's the power management or something, or system block. So maybe we connect, you know, everything revolving around power. We connect together, like decoupling, for example, bulk capacitors, crystal together, selecting load capacitance. Is it load capacitance? Either way, the capacitors for the crystal. Okay, but naturally we will start with power. Then we do crystal. What else is needed? The debug pins and the reset pin. So going back to the data sheet. Block diagram, no. Powering ground pins. So this is the one we're gonna follow, at least. And we can look at this one basically. It's the same. So we'll have some coupling capacitor on this side, the coupling capacitor on that side. Ref. ADC reference capacitance or something, decoupling. Input boxing. So then looking through here, so for example, the PTD, or no, wait, we can I put on some sort. PTA. Okay. PTA 13 down to 10, so pin 41 to 43. These are all port A. And they're just IOs 41 to 44, except for that one. Okay, I'm not entirely sure how I should read it. But I'm guessing these can be configured to just normal GPIO. 100% sure. Okay, but let's start. I mean, I'll put some color coding on these two. This one I can make like light blue. No. So, like a bit light blue. The debug, then a reset here. Some green color. And the crystal. Nice or. Damn, I keep selecting the wrong one. So, nice orange. So where do we start here? Right. We need to create our symbol correctly. Where to begin? It's tempting just to remove all of these and just create new ones. Those we can leave. So put it down here so it's out of the way. Kind of like the power always up in the top left corner. And let's see, pin 5 and pin 6. So this should be 5, and it's a power input. And this is 6. And then ground can also be at the bottom, but I also kind of just like it like this. 7, so pin 7 is ground. Then we had another one in 30, 7 and 30. Yeah. And we had another input here. That was also VDD. Pin 31. So these two pins are close together on the PCB. Copy this. Put it. Okay, whatever. I wanted to copy the picture of the footprint as well, so you could see where everything is lined up there, but it doesn't matter right now. It's not too complicated, this chip. Okay, VDD, so VDD, yes, VSS, 30, 31. And then maybe we can have the debug down here, reset also. Or pin 8, let's pin 8 is X style. And pin 9. And this maybe should be like so. Bidirectional. We should put that. So here we have all the power stuff. And a crystal could be here or on the other side. You might think I'm giving this too much thought, but it's nicer this way. It's my experience that you create your own footprint or an own symbol and set it up the way you like it, so you can get a clean design, clean schematic. Okay, then we can have PTA here. So PTA PTA PTA. I don't know. 38. That's PTA 0. 30. Right. Oh, I can add alternate pin names here. That's also nice. PTA 1, 37. PTA 2, 36. And then 3 is 35. Okay, how many do I have? 5, 6, 7, 8, 9, 10, 11. Twelve, 13. It would be better if I had let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 on the port A. 13 is 41. 35. 12 is 42. 11 is 43. Now, we'll fix it. We'll fix it. PTA 10 is 44. So these I think were correct. So, oh. So, PTA 10 was the last one, which is 44, 43, 42, 41. PTA 7. PTA 7. $29. PTA 2 and 3. 2 is 36. 3 is 35. PTA 4. PTA 4 is 48. And PTA 5 is 47. And come to think of it, I should rename this to their default function, or what they actually are going to be used for, not PTA and stuff. That's too generic. Of course. Okay. Okay. But now we have done it like this. So pin 48, for example, that is JTAG TMS or zero wire debug data IO. That we can put on here. And then this one was the reset pin. So PTA 5. Reset. Put that on there. Then pin 46. Pin 46. Damn, I should have just made all of the pins 1 to 48 and then change the ones that are not configured. So these ports, for example, that are not configured to anything, can leave that, and also then add in the future alternative pin function definition. we're making progress. We're making progress. Sometimes it takes a little bit of time, you know? Don't lose hope, fellow engineers. Don't lose hope. Take a little bit of a break too. Stretch your arms. I like to go this route where we're selecting a simpler microcontroller that only has a few pins, 48 pins in this case. A couple of them are power and ground, obviously, crystal, ADC. Oops. Hope you can hear me still. Test, test, test. Yeah. ADCs, it can be I squared C, SPI, UART, LIN, CAN-FD, or CAN and debug. But it's very simple. So I'm not discouraged at all. It's just, could have done this better from the get-go, but that's fine. Okay. I tried to do some smart filtering and stuff, didn't work out. Okay. I'll just do like this, PD1, it's pin 1, and it's not a directional, bidirectional, I mean. The next one, these ones are disabled, so I'm just adding them now by default, and then I can add alternative pin functions for them. Next one is pin 3, and I'll just add them next to each other now, so, and then I can distribute out based on which ports they are and which PTE 5 is pin 3. PTE 4 is pin 4. And then we have pin 5, pin 6, pin 7, 8, 9, pin 10. Is port D 16. It can also be configured as SPI. Next one, 11, 15. So 11 is 15, correct. And 12. PTE. Need to zoom in a bit on this. 13. Pin 12 is PTE 9. Thirteen. Fourteen. 14 is PTB5. And the PTE8 is actually by default comparator input signal 3. You know what, I'm gonna rename it PTE because it's probably gonna be left used. I don't know what you use that comparator input signal for. So leave it unused for now. Uh, 14 was PTB5. PTB4 is 15. Pin 16 is ADC. ADC single-ended signal. That's basically the entire... No, it's not. Port C, I was about to say, but... Okay, where are we? 15. 16. ETC. We don't have any use for an ADC yet. Oops. Same with this one. 17. 18. 5. C1. 19. These are inputs though, maybe. ADC inputs. By default. So maybe it's better just to keep them bidirectional. Next up, 20. Let's see, 16. 21. 15. 14. 22. 23. 24. Oh, we're getting there. We are getting there. TB1. 25. TB0. 26. PTC 27. PTC 9. 7. 28, 28. PTA 7, 29. And then we got 30 and 31. 32. What is 32? PTB 13. PTB 13, which was 32. Let's continue here. PTD 3, 33. PTD 2, 34. And then we have 35, 36, 37, 38. So I can take away. We'll get there. You know what? So we don't stop up the flow. We just continue on this side, creating them. We did skip a few since we have them here already. 31, 5 and stuff. But we're on 35 here. 35. The A. 3. 35. Oops. 36 is PTA 2. PTA 1, 37. PTA 1, 37. And PTA 0 was 38. Oops. So we got 10 more. $39. ETC 7, 39. PTC 6, 40. PTA 13, 41. 42, 43. Cheating a little bit. $12, 42, $11, 43, $44, $10. $45 is what? PTC 5. $46 is PTC 4. Some of those songs are a little bit annoying. Sorry about that. Where was I? Let's see, 46, and then 47, and 48. So maybe we just remove the rest. 8 to 9 we have here. 41, take away. Still got power. Put there. 47, 48. All right. Okay. I think that is that should be all. And now I get to go through and rename them. So this is what I should have maybe done the first time around. Add all the pins and then individually gone through them from the top to the bottom. So one down to 48. So first we're gonna do is all of these over here. And these are the pins we already know. So I will put that up like this. We have power inputs, ground, reset pin, JTAG, or zero wire debug, crystal input output, and then we'll use the rest of these pins. And PDD, for example, is currently disabled. So I'll put them here. 3 and 4 is also disabled. But the ports are close to each other, so to speak. So I keep them close to each other. The schematic, maybe I end up also moving them down. No. We keep them like this. So 1, 2, 3, 4, 5, 6 is here. 7 is down here. 8, 9 is here. PTD 16 and 15 are also disabled, but they can be configured as something else. I will just put that in now. SPI 0 as in like so. Also here SPI 0 clock. But that's cool that you get a symbol there. Okay, next one's pin 12 is also, these are put further down. E8, E9 and 8. This one is disabled. This one, comparator input. I don't know what is best, to rename it to comparator input or just leave it like that. Comparator input signal. I don't even know how it works really, so. Okay, let's move. PTB 5 and 4. So 14 and 15. It should also be up here then. them down a little bit so we get these two. Next up, PTC 3, 4. You know what? You know what? This is ridiculous. Let's take all of these, for example. So we put port A here, or we start with port A. Here's 7, here 10, 11, 12, 13. So that's port A. And some of these other ones are so 5 is the reset pin on port A. That's why we're missing some here. Same with maybe the crystal even. No, that's on port B. Anything else on A? A7. A. Okay, so B. Put that here. Any more B? Here we have lots of B. So, any more B? PTB 13. PTB. Nope. Either don't know if this is a good idea, but just trying to keep it logical a little bit. If that's possible. Okay, we go for C. Here's C, C. Oops. So, down here. 4, 5, 6, 7, 8, 9. Can I? Align items to grid. Move. Okay. So. This is the whole core, the brain of our project. Should be able to make it organized and nice so it's easy to follow. So 1 to 9, then we have 14, 15, 16. give it a little bit more space in between. So, and then the last one's PTE port. So, and then I can rather rename the different ones, put them more logically, group together, debug stuff, the crystal reset, and then leave the ports as is until I need them. I know at least that we need one of the low power UART. No, wait. What am I doing? What am I doing? So I've been streaming for 2 hours now, actually. 2 hours, 10 minutes. Soon about to end the stream. It's Wednesday. It's Wednesday. I stream again tomorrow around the same time. If you like this channel, please subscribe to it. Give it a thumbs up. If it's been fun, entertaining, educational. Really appreciate that. Yeah. So this is where we are really. The 48 pin MCU that we have selected. We've gone through all of the pins here. So I've added them based on their names. And then I will, group together JTAG stuff or zero wire debug stuff, ADC. Since it's by default, it's not disabled by default. I'll group those together, and then eventually, as we're bringing in sensors or actuators or some type of displays in the future for this controller that we're building. Yeah, we leave it as such. The ground down here. Crystal can also be here. It's good to have a bit of space too. This is going to be on one page, so we have a lot of room here. And of course, we can just branch out a little bit, make labels, and use the rest of the page for all of these. Yes. I really want to continue now. Although I've been streaming for... You know what? I will finish up this. I'll finish up this. So much fun. This one I need to put it back over here. I was itching today to get started on the MCU block. So I can go back here again and show we've done power management. So we have not a connector yet, but we have, some protection circuitry, then we have a DC-DC and LDO, and that's all in the power management block. Now we're in the MCU, or actually we'll rename that as core. Right. we're building a master, by the way, for our first project, or for our first PCB. So the master with a LIN network. And we will add a display in the future, yada yada, more indicators and everything. But for now we're on the core. We selected an XP microcontroller S32K 116, which is an automotive. MCU. So yeah, I was itching to get started with this today. Glad though that I did. Finally, that's why I want to continue just a little bit longer. Okay. So let's see. Let's go down to the debug pin. So pin 44, for instance, this one. Pin 44 can stay, but pin 44 is the JTAG EDO. And then we can move that over here. So we have it closer together. Then the PTC5, this one. PTC5, that is the JTAG TDI. Also move all the JTAG stuff together. PTC4. PTC4, this one. That is the JTAG test clock or the 0-wire debug clock. So make it a little bit bigger or wider. So maybe we put down here. So, oops. The 47 pin is the reset pin. Where were we? 46. Yeah. That's the PTA 5. That one was here. And PTA 4 is this one. Pin 48. JTAG TMS 0-wire debug data input output. So here's our debug. This is how I see it. Like logically, how it should be. We have power, then we have debug, crystal, reset, and then ground. And then on this side, we can also add more stuff on this side too, but for now, we'll just leave it here until we use them. Yeah, let's do it like that. Because if we get this part fully finished, so we work on only those pins, we have the minimum design. The absolute minimum that you need for this microcontroller to start and function properly. So we just need input rail, decoupling capacitors. Here we need 2A connector with possibly some resistors, pull-up resistors or something. Here we need a crystal, some capacitors, reset pin. We can probably connect it to some button if we want to trigger a reset. If that's the idea, or what this reset pin, how it should be configured, we'll read about that in the reference guidelines. And then the ground. That's all you need for now. And then the rest here is correct, yes. And we will also go over and select alternative pins. Right, that is our symbol. We can go back here and open the library. And we go here. We have power management libraries for LDOs, DC-DC. I messed up the naming here. This should only be core underscore MCU and nothing else. And then we have the, yeah, I could also in the future maybe make a new library called core MSU NXP and then put all the NXP MCUs and all the microchip, all the NESA's chips, depending on which one we use in the future. But for now we use NXP S32K 116. And look at that, how nice that looks. And we can, you know, put our input like something like that. And plus 3v3. Put that here. And then of course we need coupling capacitors for all of these pins. So at least 3 then. 1 for each VDD and then possibly some bulk capacitor. We'll follow the design guidelines. Here we can put on ground. But now I'm kind of getting ahead of myself a little bit. Oh. We can go back and check out this power management block, copy the text, go to the MCU, microcontroller. Yeah. So it says supplies the coupling capacitor. All VSS pins should be connected to common ground at the PCB level. All the coupling capacitors must be low ESR ceramic capacitors, for example X7R type. Minimum recommendation is after considering component aging and tolerance. For improved performance, it is recommended to use 10 microfarads, 0.1 microfarad, and 1 nanofarad capacitors in parallel. Sorry. All coupling capacitors should be placed as close as possible to the corresponding supplier ground pins. Contact your local field applications engineer for best analog routing practices. Right. VDD 5 supply. Oh yeah, pin 5 at 31 and 6 for the analog supply voltage. Ground is 30 and 7. So we need and what I'll do is I'll just go back here and then copy one of these. And just put, we need 3 for each. So the coupling. One the coupling capacitors for each voltage supply pin. And then a bulk capacitor as well here. And yeah, we should, of course, change the information here. So bulk A and D, what's the difference? Okay, that's not for us. Bulk D should be a 10 microfarad, and then this one should be 100 nano. X7R, ceramic, bulk, and the coupling capacitors. Close as possible to respective pin. So for the time being, we make it as explicitly as possible. We would possibly take this away before we ship it off for production and stuff, but considering we're working on these projects together, and it's also a learning experience, and repetition, thinking about it already now makes sense, I think. And also just keep it in mind, this is one of the most important things. Maybe not for every application, but decoupling capacitors being placed as close as possible to their respective pin on the layout is very important. How important is probably depending on the application, but just as a general rule of thumb, close as possible. And this is how we get better at PCB design and electronics design and product design, everything. We're doing it all on this channel. And since I'm really into electronics, I really enjoy doing hardware design. We're also going to do software. We're going to order the parts, do software for them, and also do testing. So we'll also set it up as a bit of a development board or debug, prototype stuff, but production. Like, we want things that we can 100% count on, and then we test it. So for example, we can test conformance testing for LIN in automotive environments. That could be cool. That could be like a huge challenge. Decoupling capacitors make the current loop between supply, MCU, and ground reference as short as possible for high frequency transients and noise. Therefore, all decoupling capacitors should be placed as close as possible to each other of the respective power supply pin. The ground side of the decoupling capacitor should have a via to the pad, which goes directly to the internal ground plane. The capacitor should not route to the power plane along trace. Right. That's what I'm saying, close as possible to respective pin. And this is the most basic stuff to remember. Okay. Let's maybe end it there. Still want to continue, but it's getting late. I need to get up, go to work tomorrow. Yeah, so then we have the decoupling capacitors. We'll of course select them appropriately. Shouldn't be too difficult. Then we can, maybe we skip this. We go to the clock. Actually, we can also move the clock up and then the JTAG stuff down. Eight and 9. This is the input, by the way, and this is the output. Then we do the debug. So reset pin and JTAG. Right, excellent. Okay, will end the stream right now. I will go and get ready, maybe eat a little bit of food before I have to go to bed, go to sleep, and go to work tomorrow. Really appreciate anyone tuning in to the stream. Hope you enjoyed it. Please subscribe to the channel, give it a thumbs up, and join me tomorrow. And then maybe we have a little bit of a pause going into Christmas holidays. But yeah, feel free to join me next time I stream. That is tomorrow, and then we take it from there, one day at a time. Getting closer and closer in our build series. Maybe I'll rename that to engineering series, because that's what we're doing. We're not just building, we're also engineering, and we'll make some really cool projects on this channel. So non-stop, full go ahead. Really appreciate having you here. If anyone watching this now or in the future, hope you enjoyed it. Until next time, bye bye.